Okay, so I'm going to talk about mental math. So, the all right. As usual, I'm going to talk about it like this. So, the first thing that I think people should ask is, what do I mean when I say talk about mental math? Like, if you're given, so mental math is this idea that you can do these calculations in your head without pen or paper or computers. Um, and there are different reasons you would want to do this. I'm going to focus on a very specific one. So there's this question of like, well, why can't you do this? Why can't you just, you know, given some random calculation, like 134 times 256, why can't you just do it? Um, and we're going to talk about how we would want to do something like that calculation, what our objectives are. So I'm going to start with objectives. So one thing that people will think about when they think about mental math is they think about doing mental math quickly. I mean, there are some random competitions with like a bunch of 10-year-olds, you know, like multiplying two 10-digit numbers together like instantly. Um, and let me show you some example of this. So there's this guy. This is some TED Talk. I think Arthur Benjamin is a combinatorialist. But let me. So you know, at the end of this, he.
Go on. Next, I do 37 squared, which is 1369, so I can say 1 billion. Take the 369, add that to light. Is there going to be carrying? No, 369, add that to light to get 420 million. Tomorrow. Okay, next we do 691 squared, that's 700 times 6.
Okay, so you can do this. I think this is not interesting, personally. So I'm not going to talk about that, right? This is sort of some pedagogical technique where you start by saying, this is maybe what you're expecting. It's not that, so that you're more attentive to the differences. If you're into this, that's great, but I can't really say anything too insightful about this because I'm not very quick at stuff like that. I think that there's another aspect of mental math, which is infinitely, yeah, for 2069. There's another aspect of mental math, which I think is infinitely more interesting. So let me talk about this in the context of maybe computer science. So I can say when computing anything, right? But we're thinking about some arithmetic computation. There are two restrictions to your ability to compute these things. There is.
I think you need to switch back to the writing.
Oh, you're right. I do. Thank you. Yeah. Great. Okay. So when computing, there are two obstacles: time complexity and space complexity. So on most modern computers, when you're doing some sort of calculation, time complexity is the thing that you really care about. So computers care about this, right? When you think about how quickly you can do anything like the traveling salesman problem or like factoring a number or multiplying numbers, it's all about the time complexity of that operation. Usually space is not a concern at all. But for humans, it's extremely different. And this is sort of just really my experience with doing mental math over the years. But for humans, I think this is the much more serious obstacle. Remembering a phone number is decently challenging. And if someone tells you a phone number once, you have a 50-50 chance of being able to remember it. So what that means is that you're extremely limited in terms of how many numbers you can hold in your head at once. And that is a huge obstacle to doing a lot of calculations. So when you're taught various algorithms for computing things, like for example, in school, you're in school, you're taught to multiply numbers, like, if you're taught 134 times, if you're trying to do this, 134 times 256, you draw this little picture and you go 6 times 4. You have a 4 here and you carry the 2, and then you do 6 times 3, that's 18, plus 2, oh, that's 20, and then you carry a 3, I guess, whatever. And you get something, and then you shift over by 1, you get something else, and then you add them up, and you get your thing. And I mean, good luck doing this in your head, because the space complexity of this thing is huge, right? So you need to remember all these numbers, and it's just not going to happen, right? It's really it's not how it works. So really, you're looking for different ways to approach problems when you're trying to do them in your head, and that's what makes mental math interesting for me. It's this algorithmic side of it. You need to come up with clever ways to compute the things you can to work around the very human limitation of the space complexity. So mental math is cool because of algorithms. Close enough. And even if you're only concerned with doing things quickly, you may still care about having good algorithms because, again, and this is not something that I want to say formally, but my experience with mental math is that human memory, accessing human memory has a very high time cost, meaning that, okay, really you can remember more than 7 numbers at once, but if you try and work with more than 7 numbers, I mean, really you can only work with like a few at a time, and then you have to like access the other numbers. And accessing for humans is really slow. Like you have to remind yourself what the other numbers were. So if you want to go fast, it's also in your interest to have good algorithms. Ultimately, if you want to go fast, like the number of algorithms you can use is pretty limited because you sort of have to know them from the get-go. I mean, if you think about this guy, right? He's just doing this one really standard thing. Like he didn't even think about how he was going to compute this product. He just had one algorithm, and no matter what number was given to him, he was going to use that algorithm. So you see, he's not really thinking about things from like an algorithmic perspective, because to think about what's special about this number and how can I exploit that to get a better algorithm than just like the fairly straightforward and generic one he's using, it would take more time than just actually using the algorithm that he was going to use to begin with. So that's the time applications of having good algorithms is not the most important, but it is present. And I'll talk more about that a little bit later. But so this is why we care about mental math. And what we're going to do is we're going to try and talk about how we can solve these problems in practice with the idea, like, you have a human brain, how are you going to do it? I mean, obviously, the more you practice something, the better you're going to get at it, but there are good ways to practice and bad ways to practice. So we're going to be talking about, this focus. So that's the end of the section about objectives. So now let's start getting into the meat and potatoes of, like, you have some problem and how do you actually do it? So I'm going to start by talking about, I think, the core of mental math, which is approximation. So approximation is sort of the most basic thing, and that if you have no idea what you're doing, this is what you want to focus on. Again, I forgot to switch back. No, I didn't. Great. Okay. So this is sort of the beginning, but it's in everything. So let me give you a very basic example. If you wanted to compute 58 divided by 4, okay, I mean, it's 14.5, but how did we do that? Well, what we did is we wrote this. I mean, the way I would do this is I would think of this as being about 60 divided by 4. And then 60 divided by 4, well, I mean, this is 15, for example, 15, 4 spans of 15 minutes in 1 hour. And then what you do is you correct. So plus correction. And the correction in this case is minus 0.5. It's minus 2 over 4. So this is how I would solve a problem like this, and this is very basic, but it illustrates the idea. So every time you're doing something in mental math, you're probably going to try and approximate the solution, and then make your approximation better and better. And this is a principle which is more general than just mental math. In fact, this permeates, yeah, this is how you always done it. A lot of modern curriculum for math also focuses on approximation a lot, and a lot of people really don't like it, which is, I think, pretty close-minded. But stuff like algorithms like this are sort of going the way of the dodo. Not that many people really keep up with what are being taught to people in like 3rd grade, but yeah, there's going to be more of a focus on this thing. It's a very natural thing to do. I guess one theme that was emphasized in section 1 is we have to play to the strengths of being human and avoid the weaknesses of being human. And this temptation to approximate, that's very much a human thing. So, I mean, let's do it. But the other thing I want to say about approximation is that this is extremely common in in just like science in general. So what I mean by this is, for example, physics, because I have some background in physics. In physics, the way you do a lot of things is you just approximate them with like a first order approximation, second order approximation, first order perturbation. If you do quantum mechanics, you've heard that term before. And really, in fact, there's this great formalism for this. I'm going to make this reasonably bold claim that this is calculus. So this is going to be our starting point for like actually doing anything. And in particular, I'm going to suggest linear approximation, which is a special kind of approximation, but it's the kind of approximation at least I do most commonly when I do mental math. So linear approximation is this idea that you have some function, say the square root function, and you have some point where you know everything about this point. And then you've got this nearby point, which is a mystery point. And you want to know about the mystery point. So how do you go from here to here? And linear approximation is a good way to answer this question. So what you can do is you can draw a line like this, and you see that the value of the line, what was I using before? I guess this, yeah. The value of the line is pretty close to the value of the mystery point. So that's going to be our linear approximation. And it's called a linear approximation because this thing is a line. Right? So I even have to zoom in, I guess, to really demonstrate. Right? See, like they're really close. So in fact, you can quantify how close you get, and you can improve that. But let's start by talking about linear approximation. So there's some formula for this if you really want to be rigid about it. I recommend that you don't be rigid about it. But if you want to be, what's going on is that if this point, we're going to call this mystery point x, and the known point a, that f of x is approximately equal to, well, if you just had to guess completely blindly, I mean, just do the most natural thing, guess that these points are about the same, right? So just guess that f of x is equal to f of a. I mean, this is not so far. For example, if someone asked you what the square root of 26 was, well, a good guess, if you had no idea at all, is just the square root of 25. Like, yeah, sure, it's about 5, right? Perfectly reasonable answer, and you should not overlook that. But it's fun and entertaining to go further than that, right? And that's sort of why we're doing mental math. I mean, mental math is totally useless in that, you know, a computer can do it. So we do it for fun, and I don't think I would have fun if I just gave this answer all the time. So let's do better. So how do we improve that? Well, what we can do is we can look at a line and we can say, what is the rate of, how quickly is our line changing, right? So what's the rate of change of this function? What is the slope of the line? And it turns out the slope of this line is 1 over 10. And there's a systematic way to compute that, but okay, it's 1 over 10. And we took a step of size 1 here, right? We went from 25 to 26. So if our x coordinate increased by 1 and our y and the slope of the line is 1/10, then that means that our y coordinate has gone up by 1/10, right? So so this number 1/10, that is a good estimate for delta y over delta x, and this this 1 is our delta x, right? So we're just doing that. And so this tells us that it should be the square root of 26 should be about 5.01. And we can continue to do better than this, but I mean, some of the fun of this is to check our answer. So let's check our answer. Right, you see it's extremely close already to 5.1. So if you just do this all the time, you're going to do really well. So the way to find these slopes is, I mean, using calculus, right? The slope is just f prime at x. And I mean, if you know calculus, you know what these are, and if you don't, just guess. It's usually not that hard to guess what this number is. But yeah, you sort of have to know calculus to know what this number is. So there's another variant of linear approximation. I mean, linear approximation is really good. And if you want to get fancy, and you know more calculus, then I can just say do higher order approximation as well, right? In general, f of x, sorry, this should be f of a, right? Yeah, much better. F of x is approximately f of a plus f prime of a times x minus a, and you know, I'm going to expand in a Taylor series plus 1 over 2 factorial f double prime at a x minus a squared plus dot dot dot. All right, so you can get a good approximation like this. You could find out how far away 5.1 is from the square root of 26 by computing the size of this the second term. So you can do that if you want. I'm not going to talk too much more about that. And so I'm going to talk about a variant of linear approximation, which is interpolation. So sometimes, suppose I asked you for the square root of 25.5. Well, one thing you can do in a sort of very natural way is just average the two answers that we got just now, right? Without having to do any linear approximation at all. We can just guess that it's going to be about 5 plus 5.1 over 2. And this picture is a little different than the linear approximation that we just drew, where here what we're doing is, okay, now we're sort of zoomed in, so this is 5, or sorry, this is 25, and this is 26, and what we can draw a line between these 2 points, and our estimate is that this point is the square root of 25.5. So this is not a linear approximation, but often it's much easier than a linear approximation because you don't even need to know the derivative, you just need to know 2 points. And of course, you can see that this is a reasonable approximation of the derivative, but I mean, it will be a little bit worse. Usually, if you're really close to one of the endpoints, you want to use linear approximation instead, depending on how accurate you need to be, whatever. But this is a common thing. So this is a good way to approximate. So this is sort of the essence of this is that whenever you're doing mental math, you're going to try and approximate things, and you approximate things using some various techniques, and this is one that's used a lot. You want to guess, you want to estimate what your answer is in terms of something easy, and then make it better and better. This idea of start with an approximation and then make it better and better. So that's what section 2 was about. All right, let's talk about section 3. So section 3 is you can't use linear approximation on everything, and you can't be formulaic, and this is what this is about. So this is I guess I'll call it ingenuity. So there are a bunch of tricks about mental math. I think the Wikipedia article has one. So let me show you this. So this Wikipedia article is terrible, right? It talks about like casting out nines. It talks about calculating differences. It talks about all these kind of like very specific and very elementary things that you really shouldn't content yourself with this. And ultimately, I'm going to talk about like why you shouldn't content yourself with like just reading this Wikipedia article. I mean, besides it being sort of poorly written and like having a bad choice of of things to talk about, but the idea is that you can't content yourself with being formulaic and expect to do well. So one way that this was captured was in Richard Feynman's autobiography, which is ghostwritten, so it's not a real autobiography. And in it, he has this story where he's working on the bomb, and so a lot of super premium physicists around him, including Niels Bohr. And he talks to Niels Bohr and describes him as having ability to do mental math, which exceeds even his own, because Feynman was already very good at mental math. And the way he described Bohr was every number is his friend. And this is, I think, an exceptionally good way of describing what you should strive for when you're doing mental math, because I think to the average reader, this seems like some sort of flowery writing, some quip, but this is really 100% on the money. This is exactly what it feels like, and this is an incredibly insightful comment. So when you're trying to do mental math, you need to look at everything that makes a certain number special and find a way to exploit it. Find a way to do something that is unique to that number, because the best algorithms are going to be about specific they're gonna leverage specific qualities of whatever numbers you're working with, whatever you're trying to do. If you try and do things in a very systematic way, you're never going to get very far. And it's challenging to hold yourself to this high standard because for any one trick, you can look at it and you can say, it's never reasonable to expect that someone will be able to do this, but that's sort of what you do have to expect of yourself. So let me give you an example, which is, I think, a fun one. So I'm going to tell you that the log base 10 of 2 is approximately 0.301. And now, based on this information, we're going to try and calculate the log base 10 of 3. And this is hard, right? There's no obvious connection between the log of 2 and the log of 3. So how do we do it, right? We have to be clever. We can't solve this problem unless we're clever. I mean, you can do generic things like just try and calculate the log of 3 independently, like a computer would. But as we talked about in part 1 about like what our objectives are, that's probably not going to go very well for you. So you need to do something that is gonna, is gonna do better than this. So one thing you can do is you can notice that 2 cubed is approximately 3 squared. And this is like really approximately, right? Like it's not very close, but it's kind of close. And so what this means is that 3 times log 2 is approximately 2 times log 3. So this would give us that log 3 is about 0.45, which is not very good. This is like unacceptably bad, but you see there's an idea behind this. So now can we do better than this? Because this is this is really not good. It's not close enough for this to be noteworthy. You probably shouldn't be satisfied with this. Like I could have just blindly guessed a number approximately this close to the answer. I mean, there are other ways you can do it, right? If you do interpolation on this, right, you get the same answer. Interpolation is you have your log, and this is 2, and up here you have 4, which you get for free, right? So this is 0.3, and this one is 0.6 because it's 2 times 0.3. So this one is, sorry, if you were to draw the line, this one down here is 0.45. But it turns out that this gap between these 2 points is really is pretty big. So so interpolation sucks here. So how can we do better? Well, can we take this idea here, recognize that it's a good idea, and do better? Well, here's one thing that we can notice, and this is really like you're just pulling this out of the blue, just making something up, and this is the kind of thing where you have to hold yourself to this high standard of you need to have like the spark, this moment of cleverness, if you want to succeed, and how much you succeed really depends on how much you can make the numbers your friends. So let me show you how I'm friends with these numbers. I can also write that 80 is approximately 81. And now we're in business, because this number, this is 2 cubed times 10, so we know the log of this. And this number is 3 to the 4. So what this implies is that 3 times log 2 plus 1 is approximately equal to 4 times log 3. So we can solve for log 3. So 3 times log 2 this is say 0.9, and then plus 1, and then we're going to divide by 4. So we have 1.9 divided by 4. That's equal to 0.475. And everyone's a mod, so someone will ban this guy, right? So we get this answer if we go about it this way. And now, okay, drum roll please. Let's check our answer. Right, so we're extremely close with our estimate of 0.475, and it was very easy. I got told my own chat rules. So you see here, by having this good idea, we can do a lot better, right? So you have to hold yourself to the standard if you want to do well. You have to have good ideas, because when you have good ideas, the calculations are very easy. So this is this idea of ingenuity, right? That you need to be clever. You need to make friends. So to finish the story about Feynman and Bohr, this book is ghostwritten, and this is a part of the book that, like, I really believe that the author, who is not Feynman, sort of made something up for this, because there's no way that the story he actually tells is the correct story. So the story he actually tells is how Bohr was able to compute the squares of numbers close to 50. So for example, Bohr could compute 47 squared in a second. He would say, oh, 47 squared, that's easy. That's 2209. Wow, look at me, I'm so good. This is extremely easy, and I would be very shocked if this were actually news to Feynman, because this is pretty simple. So what's going on here is he's writing 47 as 50 minus 3 squared. And then you can expand this out. This is 50 squared minus 2, well, plus 2 times 50 times minus 3, because that's how squaring works, plus minus 3 squared. And then the observation is that this number is 100. So this is 2500 minus 300 plus 9. And of course, you can do this for numbers close to 50 in general. Like 44 squared is 1936, right? So this is a good example of being friends with the number, but it's also such a basic example that I can't imagine that the story is literally true and that Feynman was actually impressed by the specific calculation. I do believe that Feynman was impressed by something Bohr did, but it's pretty crazy to believe it was this. But still, this illustrates the point very nicely. And in general, this is a pretty fun book to read, so if you want to go and check it out, then go for it. So, all right, let's talk about section 4 now. So there's the question, 3 was about ingenuity, and that's daunting, right? How do you have that ingenuity? So let me talk about facets of a number. So this is, I think, a way to make it more likely that you're going to come up with something clever. So every number has many components. And I'll write that down because it's important. When I say components, I mean, I guess this is what I mean by facets. So a number is some mathematical object, and like basically every mathematical object, there are many ways you can look at it, and depending on how you look at it, you sort of see different things, and the emphasis can be very different. So let me show you an example of something, going back to this guy.
Be the 4-digit number that I'll square. 1, 5, 7, 7. 1.
Okay, so right, to repeat exactly what he's doing, because we're just going to watch this video for a second, he's given a number from the audience, and he's just going to compute the square. It's a 4-digit number.
5, 7, 7. This will take me a little bit of time,
Or I guess
so
five
bear with me. 3 million. $486,929? No? Okay, wait, don't tell me if I made a mistake.
Okay, so you see here he got it wrong. And now let's see what comes next.
Was it what number was 1577? Oh, wait. Okay, let's try that again. 3 million. So far, so good. Oh, is that where I went wrong? Okay, I never make a mistake there. Okay, 1, 5, okay, 3, 1. Oh. 2 million. Was everything else right? Thank you very much.
So you see, what he did is he was focusing on certain facets of the number, but not other facets of the number. So he was asked 1577 squared, and he guessed that it was 3 million whatever. This is pretty crazy, right? Because you may or may not know that, say, for example, 16 squared is 256. So that means that 1600 squared is going to be strictly less than 3 million. So, and it seems like kind of crazy to an outside observer that this is what you would mess up, because this is like maybe the most obvious facet of a number. It's sort of its absolute value. It's just its magnitude. It's the sort of the leading digit of it is maybe the first thing you would try and estimate if you're in a certain mindset when you're faced with a problem of like evaluating this thing. But he wasn't thinking about that, right? He was thinking about what he was doing was he was doing this kind of calculation where he was writing it as maybe, I don't know, 1500 plus 77 squared, and then he was like writing it as something squared plus 2 times something times something plus something else squared, whatever. And then maybe he was like breaking these down into smaller things somehow. But the point is he was thinking about sort of this way of thinking about a number, this facet of the number, of how it's broken down into these parts, what the value of these parts are. I mean, you saw that he got every digit right but the first one. So he was viewing the number one way, and someone from the outside would view the number a different way. And let me give you an example from my own life. At some point, I was asked to calculate something very simple, 12 times 16. And my answer to this was 96. Right? Just like in like a second, this is the number I blurted out. So you look at this and you think, God, that's really dumb, right? Because clearly this number is greater than 10, and clearly this number is greater than 10. So the product is at least greater than 100. And I gave a number that's less than 100. So like, what's up with that? The answer is obviously wrong. And the person I was talking to was confused, bewildered, and like repeated himself slowly. No, 12 times 16. And I'm like, oh, okay, it's 192. So the actual answer, right, 192. So do you see the mistake I made? So, you know, I'm a number theorist, right? This is the math I do professionally. And I wasn't thinking about these numbers in terms of magnitude. I was thinking about these numbers in terms of the prime factorization. So this number is 2 squared times 3, and this number is 2 to the 4. So I'm like, wow, this number has a lot of small factors and has only one factor of 3. So 96, this number is 3 times 2 to the 5. And you see the correct answer is 3 times 2 to the 6. So I was off by a factor of 2, right? It's still a mistake on like a relatively easy problem, but it's a pretty small mistake compared to the perceived mistake of multiplying two numbers that are bigger than 10 and getting a number less than 100. So see, I was just thinking about one facet when in fact a number has many facets. And so you can apply this to problem solving in general. So let me tell you another story that came up recently with a friend. So this is an interview question for some financial position or whatever. And it's rooted in probability. So you're playing a game, and the game consists of rolling a die 3 times, a 6-sided die. So you're rolling 3d6, one after the other. So you get 1, 2, 3, 4, 5, or 6 on this one, and then 1 dot 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 6 on this one, and 1 dot 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 6 on this one. And the game proceeds as follows. So you roll this, and you either accept or reject. So if you accept the roll, then that's your score. So if you roll a 1, then you scored a 1. And if you reject, so accept is and if you reject, what you do is you move on to the next one. And then you have the same thing on this one. You roll it, and you can either accept the score or reject it. And if you reject it a second time, well, then you have to take whatever you roll on the third one. And the question was, what's the optimal strategy? Right? You're trying to maximize your score. And I mean, I don't think this is a particularly fun or interesting interview question. It's some generic probability thing, and I think you look at it and you're like, well, I could do it, but actually doing it seems laborious. But that's exactly why it's a good example for how to do mental math and the mindset you should have when you're doing mental math. So if you tried to do it in a systematic way, well, you could do it through backwards induction, for example. The average roll of the last die is 3.5. So on the one before that, somehow that influences it, and the one before that, it's again influenced. There's a lot of work. It's kind of hard to organize the stuff in your mind before you start doing the calculation. But okay, you believe that there's some argument in this way. But that's the wrong way to think about this. So and when I say the wrong way, I really mean the wrong facet. The wrong way to do it is to compute like it's homework, right? Don't do this. Here's the right way, at least in my opinion. So this question is about a game. You want to play that game, and you want to play that game optimally. So let's just pretend that you're playing the game. So you play the game, and you roll your first die, and you get a 1. What should you do? Well, obviously you should re-roll, right? If this were in front of you, this literally happened to you, and you rolled a 1 on the first roll, you'd be like, yeah, I re-roll. You don't have to think about it. If you roll a 6, you take it. If you roll 1, 2, or 3, like clearly you re-roll. So it's just a question of like using your intuition to evaluate what should you do on the 4 and 5. Because if you're actually playing this game, this is really maybe the only thing that's even a little bit confusing, right? And my intuition here, I don't know if you have the same intuition, but certainly my intuition is that should probably accept this, right? Like if I were doing this, and I roll the 5 on the first roll, I'd be like, yeah, I'm not gonna like bank on getting a 6 in the next 2 rolls. Like I'm just gonna take my 5 and be happy, right? And like it's not a particularly close decision. For the 4, I'm really not sure. My intuition isn't as strong here, but I think I reject it. I think I can do better than a 4 with 2 more rolls, or that I can get a 4 or better on 2 more rolls, and that I should reject it. But I think it's close. And this is really leveraging my intuition as someone who has played games which require probability. So if you've played, Magic or Hearthstone or like anything, or poker, like anything that requires you to think probabilistically and sort of have this judgment of what the correct play is based on, the likelihood of certain outcomes, you can use that kind of thinking that you've developed and that you've practiced to answer this question, to figure out what to do. Whereas, if you're doing it with a homework approach, it even takes a significant amount of calculation maybe to come to the obvious conclusion that you should always reject 1, right? So use your intuition is the right way. And when I say use your intuition, I mean pretend you're playing the game. Pretend you're playing the game. So my intuition is accept 5 and it's not close. And reject 4 and it is close. So this turns out to be correct. This is the optimal strategy. And moreover, someone can ask, okay, what is the EV of this game? And you can use this intuition to get the EV. And I know this because I've done it. I had a friend who, he had the same intuition. And I said, well, based on this, can you guess what the EV is? And he says, well, if you accept 5 and it's not really close, and you reject 4 but it is close, the EV is probably closer to 5 or closer to 4 than it is to 5. There are only so many things you could have in the denominator because you're not dividing by that much. So my friend just blindly guessed that the EV was 4.25 because it's a small denominator and it's between 4 and 5 and it's closer to 4 than it is to 5, so it's 4.25, and this is exactly right. So you see that by thinking about the problem in the right way, you can actually do extremely well. And it's all about finding the right mindset you want to be in to solve a problem. So if you're trying, you have to recognize what the difficulty in a calculation is going to be, and use the part of your thinking and the part of your intuition, and focus your attention on that obstacle. And if you do that, then you're going to have a lot more of the insights that section 4 says you're going to need, or section 3, right? Yeah, section 3, right? Section 3 says you have to be ingenious, and the more you leverage the right part of your thinking, and focus on the right facets of whatever calculation you're trying to do, the more you're going to be able to have these sparks that you need to do really well. Okay, so that's section 4. So this was like kind of abstract. So let's do some calculations and see how these things come into play. So section 5, right? So let's do some examples. So let's start with an extremely basic example. We're going to do 2 to the 12 plus 12 times 16. Yeah, it's this is the maximum it can stretch, in fact. So I write it this way because we know what these numbers are, right? This is 4,096, and this is 192. So I mean, 2 to the 12 is just commonly known, and 12 times 16 is something I just told you about, right? And the mistake where I said it was 96. The reason I'm writing it this way is because if I wrote it down in terms of like, 4,096 times or plus 192, then it'd be too obvious what this sum is. But instead I want to focus on something. So first of all, the fact that we know what these numbers are is an aspect of the first part, right? So in the first part, I talked about the objectives of what we're doing when we're doing mental math, and I talked about it from an algorithmic point of view. So I want to say that these two numbers are, I'm going to say, hashed. Right? You know what they are automatically instead of having to compute them. And that's extremely useful, and it's something you just pick up over time. So if you practice a lot, you're going to get it. And this lets you circumvent the extreme space limitation that I was referring to in section 1. You can cheat by knowing what these numbers are already. You can overcome the space limitation like hash bounds. The hash bounds are too American for me. I don't even know really what they are. So let me give you a hashing story. At some point, I'm at this talk, and the number 1953125 appears on one of the slides. And my boss, who's a very famous mathematician, he says, he puts up his hand just to make the comment. He says, by the way, this is 5 to the 9, in case anyone was wondering. And of course, the whole room laughs because they're all like, "What the fuck?" Like that's pretty weird that you can just be like, "Yeah, that's 5 to the 9." By the way, like factoring this number is not true. I mean, it's not that crazy. There are some hints based on the rest of the talk, based on the context that this number came up in, that it was going to have at least a high power of 5 that was dividing it. And it was a reasonable comment. He wasn't, just flexing, because it's relevant to know that this number is 5 to the 9. It helps you think about the math that was being presented in a better way. And I mean, honestly, I think the speaker probably should have written 5 to the 9 instead of this crazy number. But okay, I mean, somehow he could just like give the prime factorization of the 7-digit number just like off the top of his head. And it's like, what's up with that? So the next day at breakfast, I go and I talk to him. And I'm like, hey, that was like kind of weird. How did you do that? And his answer was basically that he had the answer hashed. He had encountered this number before, and he just knew it. What he said to me is, oh, well, you would recognize 15625. And I'm like, well, okay, sure. And he's like, well, yeah, exactly, same thing. 15625 is 5 to the 6. So he was like, well, you know powers of 5 too. And I didn't know that one, but I do know other powers of 6, or other powers of 5. So it's this kind of thing where if you just practice a lot, like if you've done a lot of the stuff, you've encountered numbers before, and maybe you remember them. I mean, now the next time that 193125 comes up, I'm gonna know what it is. Yeah. So you want to be able to hash things, and you want to be able to access that memory, and that's that's a powerful tool. So this is tying into the first part of things, that this happens, and be aware of it. Try and get numbers into this form that you recognize. So talking more about this first thing, this is, again, we have this in our head that this is 4096 and this number is 192. And adding up, this is already pushing the limit of of how many numbers we can store in our head. Like already, I think if you were to try and calculate that in like using the school algorithm, I think it would be challenging. But of course, this is extremely easy because what we can do is instead of writing this as 100 plus 90 plus 2, like we would in the school algorithm, we can write it in the much more convenient way, 200 minus 8. And this one is much easier to work with. This representation is much easier to work with than this representation. So, of course, what we can do is we can just say this is, well, it's 4096, but then we're adding 200. So it's 4296, but then we're taking away 8. So it's 4288. Very easy. So this is how, by changing the way that we represent the number in our minds, we can get around the space complexity. And this is a form of this ingenuity, right? This idea of going from here to here, or using this instead of this, is something that's like it's being clever. It's seeing a better way to do it, and there's no systematic way to do that. You just gotta see it. So now let's talk about some problem that's based off this. I've lost my mouse. Okay. Let's talk about some problem that's based on this. Let's talk about the first thing I wrote down, 134 times 256. And this is a, I thought about, talking about mental math in general before actually doing this. And so this example is like a little bit pre-prepared, but it's prepared in the sense that like I thought about it. I'm like, yes, it's the first thing I thought of. And I said, yes, that's doable. So these are like close to random numbers. But of course, these numbers are your friends, right? You know that this number is 2 to the 8. And this number, well, it's not a power of 2, but maybe what you can do is you can write it as 2 to the 7 plus 6, right? And then you can start working with it this way. There are a lot of other things you can do as well to this number. What I like to do is I like to write it as 8 times 67 times 64. Because in general, when two numbers are close together, then it's easier to multiply them. So here you see I've taken 2 powers of 2 from the 256, and I've taken 1 power of 2 from 134. And this is just, again, there are many paths to victory. You want to pick one that is most comfortable for you as an individual, so that you can sort of leverage your human abilities and also your strengths and weaknesses as a specific human. So I think this is a good one, and I'm not very scared of this multiplication by 8 at the end, and I've written it as 2 to the 3, because I think doubling things is very easy for a lot of people. So here, let's do this as 64 squared plus 3 times 64, because I think all of these things are easy. So 64 squared, we know that 64 is 2 to the 6, so oh hey, look, this is our friend 2 to the 12. And this number, well, guess what? If we move some factors over, this is 12 times 16, right? I mean, but I don't even think of it as 12 times 16. I just think this is a number that has a lot of powers. So this is our good friend 4288. So now we want to take 4288 and multiply it by 8. So let's just double it. So when we double 4288, what I would do is I would write it as 2 times 4300 minus 12. And then, well, this is easy. This 43 times 2 is 86. And then minus 24, so we have 85 76. And now we have to multiply this by 2 again. So this is going to be this is going to be 8 times 2 is 16, but we've got a 5 here, so it's going to be close to 17. So I would think of this as, so 2 times this number is the same as 2 times 8500 plus 76. And this is going to be 17,000, and then 76 times 2, well, 75 times 2 is easy, that's 150, so this is 152. And then we have one more multiplication to do, one more doubling to do. And this one is, maybe the easiest even. 2 times 17, 152. Well, 2 times 17 is 34, and 2 times 152 is 304. Because again, you just think of it as 150 times 2 plus 2 times 2. So you can do it that way. You can do it in other ways as well. I'm not saying this is the unique way of computing this product, but this is one way of computing this product. If we had asked for the similar product, 136 times 256, then we can show off a trick that goes back to Fermat. We can write, this is 23 times 68 minus 64. And whenever you have, times 64, so multiplication. And when we have something like this, usually what we can do is we can write it as a product of something plus a little bit times something minus that little bit. So we write this as 66 plus 2. So this is still the 2 cubed, times 66 minus 2. And again, this is a very old trick. This is how he would multiply things all the time. And then the reason you care about doing this is because this is 2 cubed times 66 squared minus 2 squared. And in fact, I mean, if you think about our friend 12 times 16, right, we can do the same thing. This is 14 squared minus 2 squared, which is, and maybe you know 14 squared by heart, and if you do, this is a good idea. And the reason people care about writing things as squares is because squares are pretty easy to calculate. 66 squared, you can write it as, for example, 70 minus 4 squared, which is, again, using that a squared plus b squared plus 2ab, this is 4900 minus 8 times 70 plus 16. So it's whatever at this point, right? You can do this. But so that's why a lot of people find it easier to compute squares than it is to compute general products. So this is some trick, right? Writing some product as a sum times a difference, or writing a product as a difference of squares. But when we had a 67 over here instead of a 68, then it's really tedious to do that, right? We would have to choose 65.5 as our midpoint, and come on, no one wants to do that. So that's some trick. And this sort of segues into something which I think relates to section 2 a lot, about approximation. And I guess also a little bit about section 3, which is tricks. So most people who do mental math a lot have a pool of tricks that they use. And when you look at the Wikipedia article, it's really focusing on this aspect of it. I think what I would say is it's important for you to be able to develop your own tricks and your own ways of thinking. And when Bohr talked to Feynman and gave him the squares or numbers near 50 purportedly, he was conveying one of these many tricks. But it's this idea that you can come up with tricks. That's great. Maybe rules for divisibility by 2 and by 3 and by 5. Some people know rules for divisibility by 11. Most people don't know rules for divisibility by 7, but you can come up with them. And I mean, they're not great, but you can do it. And I remember the story that I have is I had a lot of trouble with uh, computing things like this, right? I had no idea how to compute this kind of division, and I was trying and I was trying and I was talking to a lot of people, and like I don't know what to do. I don't know how to I'm stumped whenever I encounter just division, and I mean I think division is still one of the hardest things you can do, but this I mean eventually I talked to one professor, and the professor was like, I don't know, but I know this other professor who's like only here on Tuesdays, who's kind of into mental math. Maybe you can go talk to him. So I catch this other professor, and he's like, oh yeah, what you can do, write it like this. And I'm like, oh, that's smart, because now this is a geometric series. And then this side, when you write it like this, is very easy to evaluate, right? It's just 1.010101. Of course, you could have done this because maybe you know things about dividing by 9 or by 99. And yeah, you could have gotten it in other ways as well. But this you see is sort of a pretty general trick, and that it helps you divide a lot. You could have also used linear approximation to at least get this piece, right? This is linear approximation is a trick that everyone uses. Linear approximation is basically these first two terms, and then this would be the f double prime term times whatever, etc. If you actually do the calculation, it's pretty cool to see this come out. So this idea of like, oh, write it as a geometric series, I got told that. I'm like, aha, now I do this, right? Another thing that is sort of very universal, and I'm going to say this is important, is logs. Logs, I mean, they were invented to help you compute better, and they definitely do that. So I would recommend, if you want to get good at mental math, I would recommend learning some common logs, and I suggest you do a base 10. So log base 10 of 2, like I said, it's about 0.301. Log base 10 of 3 is 0.477. I'm going to start writing this log. So log of 4, you can remember it, but also it's just twice the log of 2. So it's 0.602. And then log of 5, well, again, you don't really need to remember it, because what you can do is you can say, well, the log of 10 is 1. The log of 2 is 0.301. So the log of 5 will be the difference of those things. So it's 0.699. Then log of 6, I mean, you can remember it, but again, it's just the sum of these two things. So it's 0.778, right? The sum of log of 2 and log of 3. Log of 7, well, you can remember this one, but again, you can also cheat, right? If you had to guess, what you could do is you could say that this is about 1/2 the log of 100 squared over 2. And what am I doing here? Well, 100 squared over 2 is 50, which is pretty close to the square of 7. So taking half of that will give you the log of 7. And this is really easy to compute. The log of 10 squared, not 100 squared. And I mean, this is really easy to compute. This is 2 minus 0.301, so that's 1.7, divided by 2, that's about 0.85. So you can do things like this in log 8. Again, this power of 2, so it's about 0.903, etc. So you can figure them out at this point, but I would recommend at least knowing a few of them. I would also recommend maybe it's helpful to you to learn like the log of 1.5 or something, because you don't have a lot of points between 0 and 301. So it's nice to know this. But you can also just like do the log of 15 and then subtract 1 or something. Log of 15, right? You can sum up the log of 3 and the log of 5. So you have a lot of tricks. But the idea is think in terms of logs a lot. If someone asks you for the 13th root of whatever number, don't start trying to take 13 powers of things. Just take the log of it and then divide that log by 13 and then like exponentiate it, right? Find a log that's nearby. So you can do things like that, and then there are competitions for taking 13th roots of things, and you probably do that a lot, and then you probably use like some ideas of what the last digit is using modular arithmetic, again looking at a different facet of your number, and you can figure out what the 13th root is without too much trouble. So that's that's my sort of another trick that's very, very important. And eventually, as you do mental math more and more, you're going to pick up more and more of these tricks, and you're going to come up with more and more clever ways of solving problems. And it's really extremely fun when you come up with like a new way of attacking a problem, a sort of a clever way, a way that like only works for that one specific configuration of numbers, right? Would have had to ask you 255 instead of 256, then you probably would have done something completely different. And I think that's a lot of the fun of mental math. It's always that like you're going to be attacking each problem in a completely unique way, and that's the point of mental math, is to attack every problem in a completely unique way, so you can really leverage your skills as a human, so you can leverage your friendship with numbers, and so you can see different aspects of the numbers you're interacting with. It feels incredibly rewarding. So that's sort of how I think about mental math. And at this point, I think if I'm given some sort of thing, like I'll tell you one story to sort of end the stream. Recently, I met with my academic brother. So he's some professor, and he is a student of my advisor. So that's what I mean when I say academic brother. And I go and I meet with him, and we chat. And in it, he says he needs to, we start talking about his work, and while talking about his work, the number e to the -9 comes up. And he asks me, this just comes up, and he's like off the top of his head, like, oh, how much is that? Of course, we can just take out our phone and calculate it. But I like immediately respond with about 1 in 82,000 or 8,200, which is kind of weird, right? So what's up with this? For people who don't know, E is it's some number. It's 2.71828 ... So how did this happen? How did I do this? Well, here's the idea: is I just happen to know that here I'm talking about. Normally I write log for the natural log, but I've already used log, so I'm going to write ln of 2. It's commonly known that this is about 0.7. And it's also commonly known that ln of 10 is about 2.3. So I'm not really going to use this first one. I'm writing it down so that you know it, but I'm not gonna use it for this one. But here, what this means is that if you do 10 to the 4, that's the same as e to the 2.3 to the 4. And this number, right, well, this is just multiplying 2.3 times 4. This is e to the 9.2, right, because this is 0.2 less than 2.5, and we know that 2.5 times 4 is 10. So this is e to the 9.2. And now you can use linear approximation. So you can say that e to the 9 is about e to the 9.2, and then you have this factor, right? This factor of e to the minus 0.2. And this thing, you can, well, I shouldn't write approximate, this is exactly equal, but this is approximate equal. This is e to the 9.2. Here we can use linear approximation, 1 minus 0.2. And then, okay, well, this is pretty easy. This is 0.8. So, and this number we just said is 10 to the 4. So overall, we get, this is about 8,000. And so, okay, to get the 200, you have to do sort of a second order approximation. Instead of writing 1 minus 0.2, you can write 1 minus 0.2 plus 1/2 times 0.2 squared. And then you're sort of off to the races, right? This is like, if you want to be more accurate, but it's like about 1 over 8,000. So you can do these things, right? Like you have a completely new problem of how do you evaluate what this is, and you can find some clever way of doing it. Famously, Feynman in his book talks about, surely you're joking, Mr. Feynman, talks about computing the cube root of 1729. This is a very famous problem in, like, math culture. And because he's American, he happens to know that 12 cubed is 1728. There are 1728 cubic inches in a cubic foot. So he knows that the cube root of 1729 is 12 plus, again, using linear approximation plus the power of friendship to get that this is 12 plus 1 over 432. And then it's kind of interesting to think about how you actually evaluate 1 over 432. Maybe you write this as 1 over 400 times 1 plus. So here you have 32 over 400. You can cancel a bunch of powers of 2 to get 8 over 100, and then maybe you use like a geometric series or something, or maybe you do other things. But you sort of get there one way or the other, and you have this flexibility of doing it however you want to do it, based on what you know, based on the things you've hashed, and what your strengths are as an individual. So that's sort of how you do math. You practice a lot, but you have to be mindful that you're going to have to do something that is creative and is tailored to who you are specifically. And when you're tailoring exactly the task in front of you, you want to be mindful of the things I've talked about your personal memory limitations. Like, for example, when I talk to Tig, he's extremely fast, and also I think is extremely good with numbers, in that he has a much better capacity of remembering numbers and dealing with many numbers at once than I do. So for him, a lot of these calculations that are difficult for me are completely obvious, because he doesn't need to refine algorithms in the same way to do them. So the problems that I struggle with, he can do very well, because he's just better at me in that way. So you want to be aware of who you are as a person, and how that impacts your ability, like where your strengths and weaknesses are in dealing with various numbers. You want to be aware of how you want to approximate things. You want to be aware of how you want to be clever about things, and you want to be aware of how you can look at the different aspects of a number and come up with good ideas for how to tackle the problem in front of you, and practice a lot. All right, that's it. Are there any questions in the chat? Otherwise, I'll cut the stream.